Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper machine learning. Now we are going to look at a new type of machine learning technique called semi-supervised learning. In fact, we had looked at supervised learning, and then we looked at unsupervised learning in the form of clustering, and now we are going to look at semi-supervised learning. So, the team that is responsible for creating this module is shown here. The learning objectives of this module are to understand the concept of semi-supervised learning, to discuss how it is different from other methods, why is it needed and how it is different from other methods, to discuss the different algorithms associated with semi-supervised learning, and to discuss bootstrapping, within which we have self-training and co-training. And the terminology or keywords here are unlabeled data, self-training and co-training. Now, semi-supervised learning falls between, as you know, unsupervised learning, where we do not have any labeled training data at all, and supervised learning, which we have completely labeled training data. What is the meaning of that? That the training data is sufficient to determine the labels. That is the meaning of completely labeled training data. And unsupervised, we do not have any training data. So, when we try to learn predictive tasks using both labeled and unlabeled data, but this unlabeled data, typically a small part of the labeled data with a large amount of unlabeled data. So, if you have too much of labeled data, it becomes supervised. So, what we are doing here is we have a lot of unlabeled data and a small, typically small amount of labeled data. In that way, predictive tasks will be better. So, that is called as semi-supervised learning. So, if you take labeled data and a lot of unlabeled data and you apply an algorithm to learn a model using that algorithm, then you call that as semi-supervised learning or SSL. And examples of semi-supervised learning are self-training and co-training. Now, let us take an example. Here you have labeled data. So, these data points have been given. Blue is one label and red is another label. Now, you have supervised learning. The job of supervised learning is to find a boundary between the labels. So, it is actually you are trying to find a point where you can separate the two data sets. So, that is what you are modeling. Semi-supervised, you have labeled and unlabeled data, and you will see that the amount of labeled data will be less, you will have more of unlabeled data, and you will try to fit a model in such a way that you are dividing the two. If you see here, the division is completely different because of the availability of unlabeled data itself. You would have thought unlabeled data will not contribute, it does contribute. So, first of all, the question arises, why should we go for semi-supervised? Okay, for many problems, labeled data, if you provide enough of labeled data, it can be done. Very good supervised learning algorithms can be done. But however, for many problems, labeled data can be rare or it can be very expensive. So, the acquisition of labeled data for a learning problem often requires a skilled human agent or a physical experiment, which is costly. An example of this is, suppose I want to do pause tagging, okay, part of speech tagging of the words of a document, then I should have a linguistic expert who sits and tags those for me, and I should have a huge amount of such data in order for supervised algorithm to act on the statistics of the data, or I need to do some physical experiment which turns out to be costly. So, unlabeled data is much cheaper because it is existing there in large quantity. Finding large corpus of text is not a problem, labeling it is the problem. So, this unlabeled data is easily accessible, and by using a combination of this, we can produce considerable improvement in the learning accuracy. Now, the question arises, can I do it with unsupervised? Now, the supervised puts you rigidly into a training form. Unsupervised, you go along and you try to find a pattern within the data, which we saw last time. But in semi-supervised, you are sort of focusing your unsupervised to go in the right direction. So, can we make use of this cheap unlabeled data to do our learning problem? So, let us look at using unlabeled data for supervised learning. So, you can, how do you use it? There are different ways of using it. One way of using it is you can use it to weighting the labeled examples. you can use the unlabeled data to help some algorithm like the EM algorithm, which we have not yet learned, we will go about later, to go for class specific generative models. And if problem has redundantly sufficient features, we can use co-training also, which we can use that the unlabeled data to go about doing co-training. We will come to that later. And you can also sort of detect or preempt overfitting if you have unlabeled data, because if you supervised learning always had that problem. If you have too much of data and you want to exactly fit the model, then you have this problem of overfitting. So, this are some of the cases. If you look at this figure here, you will understand it is an example taken from the journal. So, you have label instances and you have found a decision boundary without unlabeled data. Now, if you have unlabeled instances given this way, more accurate decision boundaries you are able to find in the presence of unlabeled instances. So, with unlabeled data you are able to find the correct accurate decision boundary. So, please note that the semi-supervised, the use of unlabeled data is not only because of the costliness of providing labeled data or a supervised method of data, but it is also to improve supervised learning. Now, let us look at semi-supervised learning. Example of hard to get labels is where they are widely used. Example, task is speech analysis. I have a switchboard data set, telephone conversation transcription, 400 hours of annotation time for each hour of speech. If this is so, I can use it. This is an example where it is very hard to get the annotation done. Another example is to recognize faces and images. It is hard to get lots of labeled face images, but it is easy to get unlabeled. That is not a problem. Okay. So, let us look at what this is. Let us assume this are class 1 samples and class 2 samples, and this is the decision boundary in the supervised approach. Now, I get unlabeled samples. Now, my decision boundary changes. So, that is basically what we were trying to say. So, if I have only 2 samples, I have this. I have only small number of labeled samples in this example. Now, if I use the extra unlabeled samples, I will get a better approach using this, I mean a better decision boundary using the semi-supervised approach. Now, classifier based approaches start with initial classifier and iterate and enhance them. So, you have the expectation maximization algorithm, which we will be going into later on, self training, which is the Yarowski algorithm, very famous algorithm, and code training. These are different methods. Database methods are also there. Discover an inherent geometry in the data and exploit it to find a good classifier. That is another method. This is what is called as manifold regularization. So, let us look at this. Then you have what is called as transductive learning, 2 types of semi-supervised learning. Transductive learning, that is, it does not generalize to unseen data, it does not do that. It produces labels only for the data at training time and assumes the labels, trains classifiers on the assumed labels, and then it keeps doing this. In inductive learning, what it does generalize to unseen data, but not only produces labels, but also the final classifier. So, it is a manifold assumption. So, you have transductive learning and inductive learning. Now, let us look at bootstrapping. Bootstrapping is a very, very interesting technique that has been used as a semi-supervised method. The general scheme is like this. What you do is, in the initial supervision, that is the supervised or label examples, you give seed examples for training an initial model, or you can give the seed model itself, that is the indicative features that you are going to use. These examples will be quite small in number, that is the initial supervision given. Then you classify the corpus. Here we are taking document. I will give an example with the document. Corpus with the model that you have developed, either directly given model or you got the model from the seed examples. Then what you do, add the most confident classification to training. So, whichever you found was the best, I mean you classified very confidently, that you added to the training and you keep iterating it. So, the bootstrapping approaches, there are 2 approaches, self training, which is Yarowski's method, and co-training. So, this bootstrapping, I will tell you a typical example. Suppose I have to tag a word. Okay. For simple assume, let us tag a word as a noun. So, what I give is I give it a seed sample. Now, deciding on how the seed sample representation should look like is an important issue. So, maybe I will take the previous word, the next word and its pos tag also. So, this maybe this is three component is my seed sample, and then I form a pattern. So, the pattern could be what are the noun, and before that what is the tag that came, and after that could be a pattern. How to define the pattern is also an issue. Use this pattern and find out mark all the nouns. So, that will give me exact matching, no learning has happened. Okay. Now, I take this pattern and I try to change the pattern such that using some methodology, scoring methodology, which I am not discussing in detail here, and then this is the self-training aspect, and then I get a new pattern and I keep doing this till I have finished. So, this is a very interesting and magical way of actually doing a learning problem. So, start with a few seed rules, typically high precision, low recall. That means we are not accounting for everything. Use classify to label the unlabeled data, extract new roles from the pseudo labeled data and build a classifier for the next iteration. Exit if labels for unlabeled data are unchanged, else apply classifier to unlabeled data instances and continue. So, what you start with the seed rules, use classify to label the unclassified data. Now, that classifier that you are using only in a limited sense. So, you have pseudo labeled data, use that for the next iteration, and then you go back. Okay. Now, the parameters for self training and co-training, create a pool of examples U dash, choose P random samples from U, and how do you choose? Then loop for I iterations, train CI on L and label U dash. Okay. Select G the most confident examples and add it to L. L is the number of patterns that we are using, and maintain a distribution in error. Refill U dash with examples from U and keep U dash at constant size P. So, do not increase P the number of patterns. So, this is the pool size, this is the number of iteration, pool size is the number of seed patterns you are going to use, and this is the growth size, train on select G, that is how many samples do you want to consider, that is called the growth size. So, co-training, two classifiers, you use a local classifier and a topical classifier, you use two types of classifiers, and in self-training you have only one classifier which is a global classifier. So, now let us go into self-training in detail. Self-training is a wrapper method for semi-supervised learning, and the inner loop or base learner is a supervised learning algorithm. Why is it called a supervised learning algorithm? What you have there is you take the patterns and whatever exactly matches those patterns, that is the inner loop. So, that is exact learning and it is a base learner. The outer loop is given a seed set of rules to start with, and in each iteration it uses the current set of rules to assign labels to unlabeled data, current set of rules or current patterns, whatever it is called. Some people call it rules and some people use patterns, but actually patterns can be represented as rules also. And then you assign labels, and then now you have to select those instances on which the base learner's predictions are the most confident and construct a label training set from them. So, now you have a new label training set, from that you can get a new pattern or rule. It then calls the inner loop to construct a new classifier, that is a new set of rules, and the cycle repeats. Let us just look at this more in detail. The inner loop is a base learner or a supervised learning. So, given a pattern it will just learn, or the exact learning. The outer loop is given a seed set of rules to start with. In each iteration it uses the current set of rules to assign labels to the unlabeled data. Then of that new labeled data on those instances, it will select the most confident examples and it will construct a label training algorithm. So, now you have a new classifier with a new set of rules, and then you try to repeat this from the second step again. So, a base model is trained with small or large amount of labeled data. The base model is then used to classify the unlabeled data. So, only the most confident unlabeled points along with the predicted labels are incorporated into the label set, which is called as pseudo labeled data. The base model is retrained and the process is repeated. So, you start with the base model and that base model keeps getting retrained. So, this is the process is repeated and so on. So, this is the self training algorithm. So, the input instant x and the label y. So, the learner will learn from the input space to the label y. Label data you have and the unlabeled data you have without the labels. The unlabeled data is available during training. Usually the number of labels is less than or equal to n. Then you have the test data. This test data, this is not available during training. So, this is the self learning algorithms inner details. So, one's own high confidence predictions are correct. So, the self training algorithm will predict and add to the label data set those which you feel is highly confident. How you decide that? There are many methods in which this is decided. One of the method is the pattern which is newly formed or the rule which is newly formed and which is matching with the highest number of unlabeled instances probably could be the most confident one. There are different methods in which that's called as scoring. So, let us say take an example of word sense disambiguation. Okay. What is the meaning of word sense disambiguation? Given a word, it will try to find what is the sense of the word. That word can have more than one sense. For example, if you take the word cricket, okay. So, cricket can mean the game of cricket or it can mean the bird cricket. So, the cricket has two senses. So, word sense disambiguation is the problem of selecting a sense for a word from a set of predefined possibilities. So, here the cricket had two senses predefined, one was a bird and one was the game. So, it has to decide which is correct. Here we have only two possibilities, there could be other more than two possibilities also. So, the assumption here is there is only one sense per collocation, that is you are assuming that in a sentence that word can get only one sense and one sense per discourse. So, depending upon what is available, the same sense will be given. So, self training identify all examples of the given word plant. So, create initial label data using a small number of seed collocations. Okay. So, sense A of plant is life and sense B of plant is factory. So, this is what is the initial label data set. Then train a classifier, baseline classifier, apply the classifier to the entire set. Filter and augment this addition with the trained data, seed set grows and residential set shrinks. So, repeat until there is convergence. So, what happens here is, now what will happen? You will you have life and you have manufacturing. Now, you have other life, animal, manufacturing, employee and equipment, all those come in. So, what is happening is the sets are getting expanded. So, this is the iterative updating and this is again it continues till almost all the data points have been stopped when the residual set stabilizes, that is there is no more change and it remains as it is. Now, let us go to the other aspect of semi-supervised training, which is called as co-training. You have two views of the data here. It assumes that each example is described using two different feature sets that provide different complementary information about the instance. This is quite interesting. So, what we are doing is you are having a data point and that data point can be for example, let us assume you have an object. The object can be classified according to its color or it can be according to its size. But you have to choose complementary information about the instance. Okay. So, you assume that it is described using two different feature sets and ideally the two features are conditionally independent. So, the size does not determine the color or the color does not determine the size. The two feature sets of each instance of the instances are conditionally independent given the class. Now, and each view is sufficient to determine the class, that is another assumption we make. The class of an instance can be accurately predicted from each view alone. For example, let us take a cricket ball. Okay. So, for example, if it is red, it is a cricket ball. If it is of a particular size, it is a cricket ball. So, the class can be found out irrespective of, nowadays you have white also, I am just taking that example, cricket ball. So, each view is sufficient to determine the class. Now, create small labeled training data set, train two supervised classifiers on the current training. So, using different views, use two classifier to label the residual unlabeled instances. select best newly labeled data to add to the training data. Best means comparing both the classifiers, adding instances labeled by C1 to the training data set for C2 and those labeled by C2 to the training data set of C1, and you keep iterating this. So, here in the previous example of self training, what we did is we took the most confident one and added to the same set. Here we are not doing it like this, we are having two different classifiers, and classifier C1's most confident we are adding to C2 because we are classifying using the same label, and the most confident of C2 we are adding to C1, and we are keeping on doing this. Okay, so, this is a co-training approach. You have a subset X1 and subset X2, and you do training based on the unlabeled data based on one classifier and the other classifier, and use the classification of classified examples of one to increase the subset of the other one, the training set used for training, and so on. So, this is the co-training approach, and this co-training has been given by Blum and Mitchell in 1998, and it is given this way: given the label data L and the unlabeled data U, the loop is at this: train G1 the hyperlink classifier using L, and train G2 the page classifier. This he is using it for the page rank algorithm. So, the hyperlink classifier means the hyperlinks in the page, and page classifier depending on some content. Allow G1 to label P positive and n negative samples from U. Allow G2 to label P positive and n negative samples from U, and then add these self-labeled examples to L and repeat the loop. So, let us take an example here. Here you have a text classifier and a visual classifier, and here you have the initial labeled instances. So, you have text giving a positive, visual giving a positive, text giving a negative, text giving. So, this is the initially labeled instances. Then this is separated into two as text view and visual view, and now you have unlabeled instances, and the partially labeled instances classify most confident instances of the visual classifier and label all views in the instances, and similarly retrain the classifiers. Similarly, you do for text also. So, the text and visual view you take and then you label a new instance such that both will give you the correct label. So, this is a transductive SVM or S3VM it is called. The idea is to find the largest margin. This is also a semi-supervised approach. So, you find the largest margin classifier such that unlabeled data are outside the margin as much as possible, and use regularization over the unlabeled data. So, you are given a training set T and an unlabeled set U. Find all plausible labelings U1 to UN on U. For each of the TK, T belong to UK, train a standard SVM. Choose the SVM with the largest margins. So, that is another method. So, this is the SVM with label data only. This is the unlabeled instances as you can see, and this is the S3VM boundary, which you find that the boundary is different because of the presence of unlabeled instances. If you can see, we started off with this as in semi-supervised. If you can see here, the unlabeled instances get clustered together around the positive and negative and allow, though they are not clustered, they are not labeled as such, they allow the boundary to differentiate the two appropriately. So, there are also graph based algorithms. The idea is to create a connected graph from labeled to unlabeled examples and propagate the labels across the graph. It is called the label propagation algorithm. We are not going to go into detail about this, just to say that graph based algorithms are also present, which uses both labeled and unlabeled data. There is also a semi-supervised version of expectation maximization, though we have not touched upon expectation maximization. It is a popular iterative algorithm for maximum likelihood estimation in problems with missing data. So, it consists of two steps basically. Expectation step is to fill the missing data, and maximization step to calculate the new maximum a posteriori estimate for the parameters. This is using the Bayes theorem. So, the semi-supervised EM incorporates unlabeled data into the EM. We have not talked about the working of the EM, we will talk about that later. So, you have the basic expectation maximization algorithm, you augment it with weighted unlabeled data, and you augment the EM with multi-mixture components per class. It depends on how you are going to augment the data. So, train a classifier with only the label documents or data. use it to probabilistically classify the unlabeled documents. Most examples are use documents as examples, so I mean as your data, and then use all the documents to train the new classifier. So, you are probabilistically classifying the unclassified documents. So, you keep repeating the steps 2 and 3 until convergence occur. So, this is the EM algorithm. So, you learn an initial naive Bayesian classifier F from only the label set. Then for each example D in the unlabeled, use the current classification F to compute the probability, and then learn a new naive Bayes classifier with this unlabeled with the samples got from the unlabeled also, until the classified parameters stabilize. So, this is the unsupervised clustering. Okay. Now, semi-supervised, you have data points, and this is so what happens is this unsupervised becomes, this is a semi-supervised and becomes fully classified. So, now we have spoken about and explained the concept of semi-supervised learning as against supervised learning and unsupervised learning, and then we discussed why we needed the semi-supervised learning. One was because data was not available, labeled data was not available and expensive. The second is it actually improves the performance of a semi-supervised learning algorithm also, even the performance of an unsupervised learning algorithm. And we explained the different algorithms associated with semi-supervised learning, including the bootstrapping algorithm, and we explained the self-training and co-training examples of or methodologies associated with bootstrapping. So, that is what we covered in this module. Thank you.